I guess you can see my screen now.
Yes, ma'am.
Okay. So if you remember, in the last class, we did a small derivation with the help of the Maxwell's equations and Ohm's law. We did a small derivation to see that how we did a small derivation to see that if I have a negative resistance device, if I have a negative resistance device, then how charge can accumulate inside these materials. Okay, so we finally got an expression of how if a charge imbalance forms inside a material, how it will change with time, and we got an exponential term with a mu sitting on the top where mu was the mobility. Okay, so mu was the mobility, and we saw that this mu could be positive or negative depending on you are working with a negative resistance device or a positive resistance device. That means this exponential that we have here could be a positive exponential, and that signifies a growth with time. And in case of materials where mu is negative, and we already saw that the mu is negative for any negative resistance devices. Okay, negative differential resistance we called it. So NDR, negative differential resistance devices, mu is negative. So we stopped at this point and we introduced the particular device that we are going to discuss, gun diodes or TEDs, transferred electron devices. Considered three basic properties that are essentially associated with any TED, that they are bulk devices with no junctions, okay, and they have to be made of compound semiconductors like gallium arsenide. Though I said that, but I never explained why that's so. We will talk about that today. And it operates in a region of where the electronic energy, the energy of the electrons are quite high. We call them hot electrons, which is greater than the room temperature thermal energy. So this was a gun diode, and this is the structure. As you can see, in electronics we call junctions in general when there is a p-type and an n-type, or a metal and a semiconductor. Okay, so here you have just two metal contacts on the both sides to have the terminals out, but inside there is no p-type material. It is made of an n-type slab. It is made of to make it more general, it is made of any one type of material, either p-type or n-type. Okay, so this is invented by J.B. Gunn. It was invented by, first observed by J.B. Gunn, and why it operates in this way was explained by three scientists, Ridley, Watkins, and Hilsum, by a theory which is called RWH theory, with initials of their names. So today we will mostly focus on this particular theory and try to understand that how this thing that we have learned, the formation of these charge accumulated domains inside negative resistance devices, basically gets associated and can be used to create microwave generators using gun diodes. Okay, so this entire phenomena is basically working on the principle, an effect which is called gun effect, but I will come to that later. It is better to understand the mechanism going inside first, then we will move on to understand or basically define what is the boundary of this phenomena called gun effect. So till now we just know that if I have a negative resistance device, there could be a region which we can call the high field domain. So high field domain is basically that part of that particular domain or region inside a negative resistance device which has some charge accumulation, and charge means electric field, you know, through Gauss's law of electrostatics. Wherever there is a charge, there would be an electric field. Charge, amount of charge increases, electric field will also increase. So this is the high field domain, the charge accumulation that happened inside a particular material. So this happens in a negative resistance material. Just keep that in head and let us proceed to understand the speciality of this kind of materials where you have a single n-type bulk with a two metal contacts on the both sides. And this theory, which explains this particular device, RWH theory, as I said, is also called two-valley model. Two-valley model or two-valley theory. It is sometimes called two-valley model, and you will soon understand why that is so. So this theory tells you that in any negative resistance device, you need to have a bulk solid state material, bulk semiconductors, which is usually a 3,5 compound. I am sure that you understand by now that what 3,5 compound means. Semiconductors made of group 3 and group 5 elements coupled together, you get these materials like gallium arsenide, and we need to have a material like this. Now, why so? Because you already know that gallium arsenide is a very special material, right? You have learned about it in your LED fabrication, that part also, I guess, that these materials have a very special property. What is that? What is that special property? That you have learned that if I draw the EK diagram of these materials, E along y-axis, K along x-axis, K is the wave vector, then for the same value of K, you have the top of the valence band aligned with the bottom of the conduction band. So in EK diagram, conduction bands and valence bands are not just straight lines, they are these curvy, wavy lines, and the minima of conduction band and the maxima of valence band lie at the same value of wave vector K. That is the special property of material like gallium arsenide. So gallium arsenide thus is used to make devices like LED or light emitting diodes, because if you have this particular property that conduction band and valence band have their maxima and minima at the same value of K, then the transition of electrons from one or holes from one state to other gets transformed not in form of thermal energy but in form of light energy, and you can get light out of it. So that is why we learned about gallium arsenide in the first place, because of this reason. Okay, but to understand this two-valley model, or to understand the effectiveness of gallium arsenide to make a gun diode, we have to move beyond this. So conduction band minima and valence band maxima are lying in the same value of K. But as I said that this conduction and valence band are these curvy lines, wavy lines in the EK diagram. These lines don't go just up. So they just vary like anything, and they finally can result into several valleys and several hills. Okay, so the conduction band and valence band both are like this curvy, wavy lines where you can have several valleys and hills. A nearest valley to this bottom, the global minima, let us say this is the global minima where you have the absolute minima of it, but this is also a local minima, right? If you have a ball and you strike it a little bit, it will come back here only. So this is also a minima, but this is a local minima because this is more, the value is more than this one. This is the actual minima. But close to this minima, you have another valley. This valley's value, the energy value, is a little bit higher than what we have here. How much higher? Delta E is 0.36 electron volt. So this bottom here, the energy at this point and the energy at this point are differed by an amount of 0.36 electron volt. Depending on this amount of energy difference that we have, let us call this one a lower valley and this one an upper valley, just as their energy values are low and high compared to each other. So let us call this one lower valley and this one as upper valley. Now, as the electron energy grows, electrons have more and more energy, then they from the valence band can jump to the conduction band that we know, right? So the electrons will, with enough energy to cross this forbidden gap, that is the band gap, if they have enough energy to cross this, they will jump and reach this bottom valley at first. Okay, so more and more electrons, you go on increasing the energy and more electrons jump from here to there. At this valley, we have certain properties associated to the electrons. What kind of property? Like effective mass, like mobility. These things, you have learned the definitions. I'm sure you know what mobility means, what effective mass means, right? So let us just have a look at what is the effective mass and what is the mobility of electrons which are lying inside this lower valley. So the mobility of these electrons is 8,000 centimeters square volts per volt second. Okay. Yes. Someone is saying something. Okay. So the mobility of electrons is 8,000 centimeters square per volt second here, and the effective mass is quite less, 0.068. So the mobility is high, and effective mass is quite low. Okay. Now this valley gets populated gradually as you go on increasing the energy. More and more electrons jump from here to there, and this lower valley gets populated. But as you go on increasing the energy, as I have already mentioned that we are working with hot electrons now, in electrons with higher energy. So if you move on applying more and more energy to the system, then an inter-valley transition between these two valleys start occurring. So as you push the electrons to higher and higher energy, at some point or other, they cross this hill and they reach in this valley. Okay, they cross this hill and they reach this valley. So some electrons are lying here and some electrons are here if I am considering a hot electron scenario. Okay, so let us just see what is happening here. Step by step, energy is increasing. The amount of energy supplied to the electrons is increasing. First, they are only inside valence band. Then they jump to the conduction band, but only reached the lower valley. Then as you increase the energy further, they moved on to the upper valley. But the properties that we have associated with the electrons in the upper valley is a little bit different than what we have at the lower valley. So in the upper valley, if all the electrons or any electron is at upper valley, their effective mass is 1.2 and their mobility is 180 centimeters square per volt second. So 180 and 8,000. Okay. It's way smaller than what we had in the lower valley, slow electrons. Okay, so these electrons are a bit slow. They are feeling heavy, right? 0.068 and the effective mass grows to be 1.2. So they are feeling very heavy in the upper valley. So though they have, the energy is more, their effective mass and their mobility reduces in the upper valley. So that depends on the structure of the valley, that how what is the shape and the structure of the valley. Depending on that, you can assign a value to the effective mass and the mobility. So these are facts. These are all major facts, that in the lower valley you have this much effective mass and mobility, and the higher valley you have this much effective mass and mobility. So is this picture up to this point is clear? If we understand this, then understanding the negative resistance is not going to be difficult. So no questions up to this point? Fine, I can move on. Okay, so this is something important to remember. Okay, effective masses way different from each other, mobility way different from each other, separation between the two levels remains same, that is the separation, the energy separation is 0.36 electron volt. Separation between the difference between the bottom of the two valleys. So this is the scenario that we only find in 3-5 semiconductors like gallium arsenide. This two valley picture is not present in semiconductors like silicon or germanium. This is only present in materials like gallium arsenide. So gradually the energy changes, and this is the picture that I tried to explain at that point. First, the lower valley gets populated, then some of them are in lower valley, some of them are in upper valley, and then finally all of them move to the upper valley. Okay, so now if you know that in the upper valley they are very slow and in the lower valley they are quite fast, and these are the relations that we already have. We already wrote down these relations in the last class, but again to remind you, J, the current, depends on the velocity, because velocity is basically connected to the mobility. Okay, so the current in the circuit that I will see, the current density J is connected to the velocity of the electrons V, which in hand is connected with the mobility of the electrons. Okay, so let us just stitch all these things together and see that what can I expect from here. So the effective conductivity of these systems, the effective conductivity of these systems, which is usually just Ne mu, okay, Ne mu, that was the expression for conductivity. You also derived that in the last class. Now, when some of them are in the lower valley and some of them are in the upper valley, which mu value do you want to take? Okay, you have to take something like an average, right? So that is what we do. We take the number of electrons present in the lower valley times mu of the lower valley, number of electrons present in the upper valley times mu of the upper valley. So this in total gives me the contribution of the term n times mu, n times mu. N mu E, that was my sigma, as I derived in the last class, you also did that with me. N E mu, it was the expression for conductivity, but N mu, we cannot exactly pinpoint the value for mu or N here. So we segment it that some of them are present in the lower valley and some of them are present in the upper valley. Thus, the total conductivity should behave something like this. So that simply means the conductivity basically depends on how many electrons are in the lower valley and how many electrons are in the upper valley, because mu values are drastically different in both the cases. Okay, so let us see that what can I expect. Let us see what can I expect to be my IV characteristics, or to be more specific, IV characteristics are basically same to J versus E graph, right? Because J is the current density.
Ma'am, could you go to the
Yes?
previous slide just once, ma'am? Just go to the previous slide just once, ma'am.
Yes. So here we are just talking about the effective amount of conductivity when some of them are in the lower valley and some of them are in the upper valley. Okay, so we have to assign a value to the effective mu that I get out of it and the effective number of N. So electron density in the lower valley is N L and upper valley is Nu, and Ne plus NL plus Nu is basically the kind of the total effective electron density, and mu is electron mobility, which is different in the both cases. This is the effective conductivity. Now you know that J is equal to sigma E, right? That is my change form of Ohm's law. J is equal to sigma E. So this is basically equivalent to having our IV characteristics V is equal to IR. Okay, so V is equal to IR. If I plot I and V together, then the slope tells me what is the resistance. Is it positive or negative? Depends on the slope. So if I plot J is equal to sigma E, I plot J versus E, then conductivity will reflect the same thing that as the resistance should reflect, right? So let us see that how J versus E graphs look like. So J is equal to sigma E, but sigma is now given by this expression that I have just wrote there. E came out and then mu L NL mu U Nu, depending on how many electrons are in the lower valley and how many electrons are in the upper valley. Okay, and now you can guess that what will happen now. So to begin with, there was no one in the upper valley, right? Upper valley was completely empty. We are in the state like this, where no one was in the upper valley. So the number of electrons were growing constantly because electrons were jumping from valence band to the conduction band as the energy increased. So NL, the number of electrons in the lower valley, was only increasing at that point in time when the energy was quite less. Okay, and none of the electrons were in the upper valley to begin with. So that is the first segment of the graph that we get, this segment. Okay, so in this segment of the graph, we see that this entire term, this second term, was absent there because none of the electrons were in the upper valley at that time. Only the number of electrons in the lower valley was increasing, and thus if this is the term that is increasing, then the effective slope is also that is, the number is growing. So you are getting a steady increase in the graph, right? So the J and sigma E, so the graph was increasing like this. So in this part, only one mu was playing its role. Only one mu was playing its role, and thus the slope is fixed. Okay, only one mu was effectively playing its role to control the slope of the curve. Now, if all the electrons are in the upper valley, let us consider this case. When all the electrons finally, for higher values of energies, all of them will be in the upper valley, then at that point in time, when all of the electrons are in the upper valley, then only this term is going to contribute. And only one mu is going to contribute at that point, and that is this mu upper. And this entire term will not have any effect if all of them are in the upper valley, this case. Okay, if all of them are in the upper valley, then mu L has nothing to do there. Okay, so J is equal to sigma E will give you E mu U N. Okay, so you get a different resistance, that is a different slope, but this slope the slope that you expect for the case where all of them are in the upper valley, because the value of mu u, as I pointed out earlier, the value of mu u is order of magnitude smaller than that I have in the lower valley. Okay, it's order of magnitude smaller. That means the slope that I will get will also be quite small compared to the slope that I expect when all of them are in the lower valley. Okay, so what is the intermediate state? The intermediate state is that some of them are in the lower valley and some of them are in the higher valley, this one. Okay, so as the switching goes on, then at some point or other, this graph should start bending, and the effective mu value will try to get this value so that it comes closer and closer and closer to this scenario, right? So effectively, as the numbers in the higher valley will increase, I will slowly tend to have a graph where this straight line behavior will be expected, because that is what we expect when all of them are in the higher valley. So in between, what happens is the graph suddenly at some point it starts turning and it bends downwards as the effective mu changes. Okay, effective mu changes, it starts reducing because it's like a weighted average. So some of the electrons now have very slow velocity and they are not contributing that much. So the expected slope that we used to have will start reducing, and we will get this region where the graph starts falling with respect to E. Or in the IV characteristics, you can expect a resistance is going to be negative. Yes, yes. Yes. Questions? Any questions?
Why do we have an increase in the resistance again after EU? Means why do we get positive again? It should go all throughout negative because the mobility is reducing.
But when suppose all of them were in the upper valley only, then you expect a straight line graph like Ohm's law,
yes,
right?
Yes.
If all, so that is this straight line. This is the straight line with the lower slope, and this is the straight line with the higher slope. If all of them in the lower or all of in the higher valley. So at some point or other, this transition should occur, that the slope will reduce constantly and reach this other graph where the slope is quite small. Okay, because so that is what is happening, and this is the source of the negative resistance region in our gun diodes. So in our gun diodes, you have this beautiful behavior. Even if you see that how the velocity is changing with electric field, you are going to see the same behavior, because velocity, the drift velocity, is basically E times mu, right? Mu is defined as V by E, that is the average drift velocity of the electrons, and that velocity is going to reduce, because in the higher valley all of them are really slow. So effectively, if you have some runners together, 100 of runners are running, some of them are gradually turning to be really slow, then effectively for the population the velocity becomes lower and lower, finally when all of them become very slow runners. So just consider a population of people running where after a particular interval some of them are losing their speed really rapidly. Okay, so that something like that is happening. So this is the graph that basically gives you the behavior of mu, because you already have seen that mu is also going to be negative. So that's why this is also an interesting thing to observe, that here you see that dVd that is how drift velocity is changing with electric field, that gives you this differential mobility, right? And that is also negative. So this is the proof that you have this negative resistance region where you have this negative mobility associated with the system inside these bulk devices or gun diodes. Okay, so as soon as you see that there is a portion where you have this negative mu, as soon as you see that, you can associate this directly to that equation of Q where charge accumulation was taking place, right? That was the point where we stopped in the last class, and you have seen that with time, the charge will increase, if exponentially increase, so to say, exponentially increase if you have mu negative, which you have for a quite large region in these materials where this particular behavior is happening. So the materials for gun diode is really important, and they are basically the key because the band structure is basically guiding the entire thing here. So what are the points that we have to remember to choose a material to make these devices? To make these devices, I have to take care of three things. First thing, energy difference between the two valleys must be several times larger than the thermal energy, so that the thermal energy is enough to make them switch from one valley to the other. So the energy difference must not be very, very high. The energy difference between two consecutive valleys, the lowest one and the upper one, have to be several times larger than the thermal energy. Energy difference between the valleys must be smaller than the band gap energy. The energy difference between the two valleys must be smaller than the band gap energy. Here also you have seen that the energy difference between the two valleys were of the order of 0.03 electron volts, and the band gap, as you know, it's of the order of 1 electron volt, 1.3 electron volt, something like that for these semiconductors, right? So the difference between the valleys, energy difference, must be smaller than the band gap energy. And the most important one is the last one. The most important one tells you that the lower valley electrons must have higher mobility and smaller effective mass, because that is the key. That is the reason that you have the second graph, the upper valley graph, having quite a less slope than the lower valley graph. So to ensure that the negative resistance region, you must ensure that electrons in the lower valley electrons must have higher mobility and smaller effective mass. This is why we have to be very particular to choose these 3-5 elements like gallium arsenide, indium phosphide, and so on. These have all these 3 key properties necessary that are necessary to make a gun diode. Okay, according to the theory, this actually suits. These are the good candidates which actually satisfy all these categories. Okay, energy difference between valleys must be larger than thermal energy. Energy difference between valleys must be smaller than the band gap energy, and the lower valley must have higher mobility. That's it. These 3 things we have to remember while choosing the material. So now let us say what gun effect is. Gun effect is basically that when you have such a material like gallium arsenide, an n-type gallium arsenide, and put it through a really high electric field, that is, you are applying quite high energy, right? You need energy to make these electrons move to the upper valley. Then at some critical point, at some critical value of voltage, suddenly some oscillations in the current starts occurring. So suppose you have had a gallium arsenide sample and you are applying some voltage across it. Then for lower voltages, nothing happens. As the voltage goes higher and higher, suddenly the current starts oscillating like this. Okay, and these oscillations that you see here, can be exploited to make microwave oscillators. Okay, these oscillations we exploit it to make generators or microwave oscillators. But what are these oscillations? Why are we seeing these oscillations? The reason is the higher charge accumulation that we will see in the negative resistance devices. As soon as you apply more and more voltage, then you reach that portion in the IV characteristics or the drift velocity graph that I have shown you.
Ma'am, if you put, I didn't really get what the gun effect, when the gun effect happens. If you put gallium arsenide in a high electric field or in a high voltage.
If you put gallium arsenide, if you apply quite a high electric field across a gallium arsenide slab, say an n-type gallium arsenide block you are applying a very high voltage across it. Then when you apply that voltage across it, hello, am I audible? Can you hear me?
Yes, ma'am.
Yeah. So if you apply a certain voltage above a critical voltage, then suddenly you see these oscillations. This effect is called gun effect. Okay. This is the first observation that Gunn made. J.B. Gunn was doing an experiment with an n-type slab, and he saw that as you go on increasing the voltage beyond a certain voltage, suddenly you see these oscillations. Now, why these oscillations and what are these oscillations? Now you can understand that once I reach the area where mu is negative, the effective mobility of the carriers is negative, then immediately inside the slab, these high field domains that we explained in the last class, they start happening. So the entire material becomes a bit unstable. So you can say that the entire material becomes a little bit unstable. And if you have some charge imbalance for some reason, if you suddenly some charge imbalance occurs at some place, it grows suddenly, it grows and it becomes a high field domain. So it has been seen that if you have a high field a portion where huge number of electrons have suddenly accumulated, then that portion will be very highly attracted to the positive terminal of the battery, right? So if you just connect a battery across this device, if you have an N-type material and you connect a battery across this device, and frequently, very frequently, these high field domains get created inside this material, that domain will quickly run to the negative side of the battery and go there. As soon as this huge number of electrons reach the battery, the end of the battery, you will have a sudden spike in the current. Again drop. Again, after some time, again another high field domain will reach, and you will again have a high current, and again a drop. So this will go on because the entire material has become unstable, and very frequently some high field domains are being created near the positive terminal and they are rushing towards the negative terminal. As soon as they reach there, you get a suddenly high current and again a low current, again suddenly high current and again a low current. So this goes on happening, and you see these oscillatory frequencies occurring across a gallium arsenide sample if you apply quite a high field. Okay, so let me just yes, so let me just yeah, so yes, so once you apply this enough field, then immediately this oscillation start getting created, and these oscillations, the frequency, the period of these oscillations are basically dependent on the length of the sample, because the high field domain has to travel through the entire length of the sample and reach the other side of the battery. So you have, say, this block of gallium arsenide, and inside that a high field domain has been formed, and that is basically nothing but a crowding of electrons. So this is a crowding of electrons, and here you have a positive side of the battery. So they will quickly rush towards the positive side of the battery, and once they reach, you will have a spike in the current, and again once they reach, again you have a spike in the current. Continuously these domains will get formed near the negative terminal of the battery. Continuously they will get created, and these, after getting formed, will rush, and you will have these spikes occurring. Okay, so this depends, because they have to travel the entire length of the sample, this depends on the specimen length, that how long your sample is. By controlling the length, that actually controls the transit time, that how much the electrons will take from moving from one electrode to the another electrode. You can control the frequency, and if you can control the frequency of the oscillations, you can make any wave coming out of that. So the current that you see can oscillate at any frequency. You can control it by controlling the specimen length. So this is the entire operation of gun diode, gun effect, and how this phenomena occurs on the basis of, yes, question. Okay, so try to just join all these threads together, whatever we have discussed. Okay, the high field domains, the formation of negative resistance due to the two valleys, and how that can be coupled together with the understanding of transit time and the specimen length to make transmitters or oscillators. Okay, so you can make oscillators, power oscillators, microwave receivers, microwave transmitters, radar transmitters using this gun diodes. They are hugely applied in air traffic control, and these things, they are being hugely applied. Okay, so that is basically how these things work, and how you can make microwave oscillations, microwaves, from these devices. Okay, so I will stop at this point. If you have any questions, please ask. So you take your time, okay, study this entire thing. If you have any questions, just let me know in the next class. We will just finish up on this particular module in the next class. Yeah, I will upload the notes to this, and it is good to study from these notes because I just accumulated many things from many books and stuff. So it will be better if you study from here, and just keep a track of all the equations that we have used. They will come in handy to solve problems related to gun diodes. And only one negative resistance device is still left, that is the impact family. We'll talk about that in the next class, and I hope to finish that in the next class if possible. Then we'll be done with our syllabus. Okay, so see you in the next class, and with the hope that we'll be finishing it up in the next class. If not, then maybe one class more. Okay, chalo fir, see you in the next class. Bye.
Thank you.
Thank you, ma'am.
Thank you, guys.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.